Okay, let us now show the general theorem that, look at the statement, any graph with all degrees even, any graph with all degrees even will have this property that it will have an Eulerian circuit in it. Okay, any graph with Eulerian circuit is called simply Eulerian graph. Alright, so all I'm saying is any graph with all the vertices having even degree will have this property that there will be an Eulerian circuit. Now, what should we show? You give me a graph and you ensure that degree of every node is even, then you need not show me explicitly an Eulerian circuit there. It is understood there is one there. Okay? And let's see how this is true. Let us go slowly. Now, the proof involves a very subtle strategy that requires some explanation with some real life analogy. Okay? I'm going to tell you all a story to begin with. Most of you would have studied this in your school days if you are from India. So there is this story of Tenali Raman, who was a minister in the court of this king called Krishnadevaraya. He was both humorous as well as intelligent, and Krishnadevaraya would ask Tenali Rama to solve his problems almost all the time. And Tenali Rama would come out with very ingenious and very comical ways of solving Krishnadevaraya's problems. There was one fine morning where Krishnadevaraya sees two women enter his court with a small kid, fighting that this kid is mine. The kid is so small, an infant, that Krishnadevaraya could not ask the kid, "Who is your mom?" as the kid wouldn't speak, given that it is an infant. Krishnadevaraya is perplexed. He doesn't know whose kid is this and who is the mom of the kid. And so as and always, he says, "Tenali Raman, please solve this problem." And Tenali Rama, as and always, comes out with a very neat way of finding out who is the mom. He goes sweetly towards the kid in the pretext of cuddling the kid, and then pinches the thighs of the kid very hard. So you all know what happens when you pinch an infant. An infant starts crying incessantly. And the moment the infant starts crying, one of the two moms starts crying as well and comes and hugs the kid first. And the second mom has absolutely no reaction. And from this, Tenali Raman concludes that here goes the answer, Krishnadevaraya. You all now know who is the real mom. Now, let's analyze the story. Tenali Raman brings in a noise in this scene where he goes and seemingly unnecessarily pinches the kid, just to ensure that this becomes a litmus test to understand who is the real mom. And then after pinching, he understands that it's a damage to the kid. It's being violent to the kid, and then he even massages the kid or malcajoles the kid and ensures that the kid feels better. Right? So he brought in a factor and then removed that factor. Correct? To understand what is what. Similarly, in our proof, I'm sorry for having told you a very long story, but I could not find a good analogy because this proof involves a small technique which is very confusing, and the technique comes very close to this story strategy where you add in a new noise which is seemingly irrelevant and then remove that noise back again, and there you are, boom, you get an answer in your hand. So what is this? What is the parallel between this Krishnadevaraya Tenali Raman story and the proof in our theorem? You will get to know when I go there in the right place. I'll tell you how it's analogous to the story of Tenali Raman. Now look at this. You are given a graph with all the vertices being even degree. Let us take one node, some node, namely x, you know for sure that it has at least two edges going from it. Why? Because its degree is even. Its degree is even means what? There should be at least two edges going. And please note, these graphs are connected. Any connected graph is what we wrote. Any connected graph with all the vertices having even degree will have an Eulerian circuit. Let me take one such vertex X, and I can guarantee you that it is adjacent to W1 and W2. Right? Now, what I do is I connect W1 and W2 and then remove this edge XW1 and XW2. I simply remove it. So when I remove it, you get a new graph altogether. This is not the graph that was given to me. Now my graph G has become G dash. How did it become G dash? You removed a couple of edges and introduced a new edge. Let us observe this carefully. What happened to degree of W1 remains the same. Why? Pause and think. What happens to the degree of W2 remains the same. So W1 was even and continues to be even in the new graph G dash. What was the degree of X? It was even, and you remove some two edges. It might have more edges too. Right? You simply remove two edges. When you remove two edges from a node with even degree, it continues to have even degree. Okay? If it had only degree 2, then it becomes an isolated vertex. It is not part of the graph at all. Right? Or if it's adjacent to other vertices, it will be part of the graph. Now what I do is, I know very well this G dash has as many vertices as G, but one edge less. Why? Because you removed two edges and added a new edge. So from G you went to G dash. Correct? So you have one edge less. Now, think about this. What is induction? Induction is all about if you can show that something is true for step K, and if you can show that it's true for K plus 1, then it is true in general. Now, I took a graph with some M edges, let's say. Now it became M minus 1 edges. So let me apply induction here and say it is true for M minus 1 edges. What is true? A graph with M minus 1 edges with all degrees even has a Eulerian circuit, which means there is an Eulerian circuit on G dash. So what I will do is I will construct that Eulerian circuit, observe it carefully, and I see that it starts from W1, goes around and ends in W1. And eventually it would cross W2, W1 also. Right? What I will do is when it starts from W1 and crosses W2, W1 somewhere, this edge is basically, all I'm saying is it will cross this particular edge and all the edges in fact when you start from W1. Correct? Now, whenever you start from W1 and come to W2, all I do is I will not consider this edge from W2 to W1. I will make these two edges reappear instead, and I'll go to X and then reach W1. I repeat. See, there is an Eulerian circuit starting from W1, going around everywhere and then coming to W2 and then ending in W1. Correct? When you start from W1, finish all the edges and come to W2, you don't take W2 to W1. You have a twist in the story. You go to X and then come to W1. That way you show that you exhaust all the edges in the graph G. Please note, G dash simply had one edge included and two edges removed. In G dash there is a Eulerian circuit. So you use that Eulerian circuit to obtain an Eulerian circuit in G. Correct? I repeat, the structure of the proof is very simple. Given a graph G, take a node X. It will have at least two vertices adjacent, namely W1 and W2. That's because it has even degree. Correct? And then what you do is you take XW1, XW2 and then remove these two edges and join W1, W2. Right? When you join W1, W2, you observe that you went down by 2 edges, but you included 1 edge, which means the deficit is 1 edge. You lose just 1 edge. When you lose 1 edge from M edges of the original graph G, you come to a smaller graph with M minus 1 edges, which is G dash. And in G dash, given the lesser number of edges by induction, there is a Eulerian circuit. Right? There is this Eulerian circuit. Correct? Why is there an Eulerian circuit? Because it has lesser number of edges, and hence there is an Eulerian circuit. And after you see this Eulerian circuit, what you do is you know that there is a way in which you start from W1 and end in W1, and somewhere W2, W1 also comes in that Eulerian circuit. So what you do is, whenever that edge comes from W2 to W1, instead of that edge you put W2 to X and X to W1, and bingo, there you are. In the original graph G, you just found an Eulerian circuit. Now, what was the analogy for? You see what I did? I removed a couple of edges in the given graph G. I brought in some new kind of noise. I included an edge W1, W2. Why on earth did I do that? I will be getting a different graph altogether. If you asked to solve a problem in your house, you should not go to your neighbor's house and then solve their problem, right? This sounds something like that. Instead of solving the problem in my graph G, I go to some other graph G dash, but then when you go to G dash and then solve the problem there, you observe that boom, the problem gets solved in G. Why is that? That's because G and G dash are just 1 edge less, and you are able to apply induction there. You see, this is very, very analogous to your logarithms. You see, when you apply logarithm, multiplication becomes addition, and you simply add there. When you add there, you don't get the answer. You should take the anti-log and you will get the answer, right? So this is just like that. From the world of G, you go to the world of G dash, you solve it there using induction, and then come back to G, and you see that you indeed have solved the problem. So Tenali Rama's story is just to tell you people that adding some noise and then removing it sometimes helps us get to the solution. Well, what we did not observe in our discussion so far, we had a long discussion. You see, for almost 10 to 15 minutes we discussed how when a given graph has all nodes even degree, there is always a circuit that exhausts all the edges, also called the Eulerian circuit. There was a small point in the proof where there were 2 cases. I didn't want to disturb your minds with considering all the cases there. Then the cases become more important than the proof itself, right? So I kept it for later discussion. Now, when you remove these 2 edges XW1 and XW2, you might end up having a disconnected graph, right? So there could be a component with this X completely away from this side. In that case, edges of course will go less by 1, but it will be a connected component with even fewer edges, and hence there will be a Eulerian circuit on this smaller component. Now what I do is I finish that Eulerian circuit, and then again the same logic, W2 to W1, and then I have finished an Eulerian circuit on W1, but instead of W2 W1 I remove that edge and I put back these 2 edges. So which means I go to X and then go to W1 and I end there. But then when I go from W2 to X, what I do is in this component also there is a graph with all nodes having even degree. You see that, correct? Why do all of them have even degree? By hypothesis, the graph has all vertices with even degree, right? And this got disconnected. The smaller component, by induction, even this should have an Eulerian circuit. I go to X and boom, I travel this entire place and then come back to X. That's possible. Why? The graph is Eulerian, correct? So it's a smaller graph. So I come back to X and then go to W1. I repeat, when you remove these 2 edges and put the edge W2, W1, this component can get disconnected, and then what you do is you find an Eulerian circuit in this world, and when you find it out, you will have an edge going from W2 to W1. You remove that and you put W2 to X and then X to W1, and when you do that W1 to everything, boom, you finish it, then come to W2, and then vroom, you go to X, and then before going to W1, you exhaust the Eulerian circuit on this component, and then go to W1. And hence, the case when the graph gets disconnected is also taken care of. Now, if this is very clear to you, then know that you have actually missed some point somewhere, because this is something that should be not at all clear to you in your first attempt of reading, given the lot of chunky facts here. There are a lot of fact 1, fact 2, fact 3, fact 4. We are using induction, we are using that noise reduction, the Tenali Raman example. You must be wondering, Sudarshan just lectures a long video and calls it a proof. But yes, bear with me, this is one of the upper bounds for hardness. You see, no other result is as hard as this. That's because it's a very involved theorem. This changed the world of mathematics. People started believing that something as silly and as simple as Königsberg Bridge question can have some deep math associated with it. So you cannot solve the Königsberg Bridge problem because of this theorem. You see, if you want to traverse a given graph, it must and should have all nodes even. Here is the case where Königsberg Bridge is the case where not all nodes are of even degree, and hence you will not be able to traverse that. That is one way of saying it. But then what is it that you can traverse completely? By exhausting all the edges, such a graph should have the property that all nodes are even. Only then you can traverse. Right? So it takes some practice. Maybe you may want to watch the video again and again. Please email us in case you have questions. If there's a better way to explain this, I'll try to do it once more maybe. But here is my best at this given point of time. So it'll probably help you if you can write some non-trivial graphs on, let's say, 10 nodes, ensuring that every node has even degree, and try to see if this theorem's proof helps you in observing an Eulerian circuit there.